Orko, what is the meaning of right direction?
Anything which reduces my distance towards Majnu material.
Exactly, right? I mean, isn't it logical, right? That right is that, that reduces the gap, okay, towards your goal, which is in this case Majnu ka Tila. In general case, in an optimization problem, basically this is the gap, isn't it? X of t minus f of x star, this gap keeps on reducing, right? I mean, this is the broader sense of right direction, isn't it? Anybody has a problem here? Is it clear? Right? The idea is to go in a direction which gets me as close as possible to my optimal solution. Okay, but here is a problem. Okay, when I want to go to Majnu ka Tila, I know I want to go there, right? My x star is known and my fx star is also known, right? But if I knew the optimal solution beforehand, then why would I go there? I'll just put it there, na? Isn't it? So what is the so Shantika, question is this. Shantika, you are here?
Yes, sir.
So I don't know fx star. Then how do I know that I am getting closer to fx star? So I know xt, which means I can calculate f of xt, right? Okay, isn't it? So I know xt, so I can calculate f of xt. I can calculate gradient of f of xt and all that. Okay, but I don't know fx star. I don't know this x star. Then how do I calculate fx star? And then how do I calculate fxt minus fx star? Is the question clear, Santika?
Yes, sir.
Batao.
So, sir, we move in the direction where the gradient is getting reduced.
Why? Gradient is getting reduced.
I mean, del f of x.
What is the meaning of reduced?
I mean the slope is towards the. I mean, slope is. Until the slope is 0.
No. Where is the slope 0 coming? How do you know that? How do you know that when you go from x0 to x1, slope is getting reduced? You're saying that you'll measure the gradient at x star, and then you'll measure the gradient at f of sorry, you'll measure the gradient at xt, and then you'll measure the gradient at x of t plus 1, and you'll see whether the difference is getting it's getting closer to 0. That's what you're saying?
Yeah.
But how do you know that when you go from xt to xt plus 1, the gradient will become 0? Because when you go from xt to xt plus 1, there are infinite ways of going from xt to xt plus 1, isn't it? Right? So I'm here. Let's say I'm here. I'm at xt. Now I can go this side, I can go here, I can go here, I can go in all possible directions, isn't it?
Yeah. Actually,
So
sir, the function value reduced. I mean, f of x reduced.
I understand, but I'm saying that how do you know that when how do you pick a direction such that it will reduce? You'll not go in all possible directions and pick the one where it's reduced, right? That is that's exhaustive search at every point. Yes, Rohan?
So can we say like if the slope is positive, then we'll move towards the like seeing the graph that then we'll move towards the left. If it is negative, then we'll move towards the right.
Kind of, just that when you have a objective function with with n-dimensional variable, right? F of x, then there are exponential as many directions where you can move, and the notion of slope is not even there, because there are even the slope, the gradient is of n dimension, right?
Yes.
Then you're getting the point, na?
Yes,
You're right.
but
You're absolutely right.
Yeah,
Huh.
so still, but we know that the direction of the gradient is where the maximum decrease happens. So
The direction of the gradient is where the maximum decrease happens. Okay, actually it's the opposite. But let's see what.
right. Sorry, 180 zero. Sorry.
Huh. So Anup, carry on.
So the direction
Yeah,
of the
opposite.
gradient is the direction in which if we move, our function will increase the most. So if we just move opposite to that, our function will decrease the most. So that's why we will move in the direction opposite to the gradient.
So the
Yes, sir.
answer is absolutely correct. But how do you know that, Anup? Can you
So,
prove that?
so actually, it was in maths 3 in the course that the direction of the gradient is the direction in which function increases the most.
So can you give me a very broad proof? Whatever. I mean, whatever you remember. It's totally fine to really remember even a wrong proof.
So actually, like the directional derivative at a point is like the dot product of the mod of two, and there was a cos theta term involved. So if I don't actually remember that proof.
No, but you're going in the right direction, so to say. So directional derivative. ठीक है. Okay. Yeah, Siraj.
Yes, sir. So the directional, मतलब किसी भी direction में derivative is the dot product of the gradient at that point into the direct unit direction vector. Now we know that the dot product of any two terms is maximum when they are at like they उन दोनों के बीच का angle 0, so they are in the same direction. That is why we know that the change is in the direction of the gradient. Directional derivative will be maximum if we take the direction of the gradient itself. That is why we say that the maximum change in the function will be in the direction of gradient.
Okay, great, right? So here is a small poll I want to run. So how many of you, okay, how many of you know the meaning of directional derivative? You can raise your hands if you don't know. I want to see. Yeah, how many of you know the meaning of directional derivative? Just raise your hand. Those who don't know, just raise your hand. All of you know? So जिनको नहीं पता है, are they raising, और जिनको पता है, they are raising?
Sir, I don't know.
Yeah, so those who don't know, please raise. Okay, those who don't know. So Zubair, do you know the meaning of directional derivative?
Yes, sir. I mean, it is the differentiation. The differentiation of a function in a particular direction.
Differentiation of a function in a particular direction. Okay. Tushar?
Sir, I don't know. I just lowered my hand like after you took a look at the.
Okay. All right. ठीक है. So you guys can just lower your hands, or I can make you lower your hands also. All right. So yes. So the answer is that Siraj and Anup etc. had given is correct. Okay. But what is the they've given a correct answer to what? They've given a correct answer to this question, that what is the meaning of right direction, right? Go in the right direction. And they're saying that, well, when I go from xt to xt plus 1, go in the direction of go in that direction where the rate of change of decrease of function, right? So rate of decrease of function, not rate of change of decrease, sorry. Go in a direction. So let me just write it out here. Okay. So the meaning of right direction is, okay, where rate of decrease of the value of function or rate of decrease of function is, I'm using a term locally, okay, maximum. Okay, this is the answer. Okay, so I am at xt. Okay, I am at this point xt. Okay, I can go here, I can go here, I can go anywhere, right? I can go any of these possible directions. Okay, so the answer is that I'll pick that direction. Okay, I'll pick that direction. Maybe this is the direction. Okay, I'll pick that direction where at that point xt, at that point, the rate of decrease of function is locally maximum. Look, I don't know what's going to happen later. Okay, but at every point I'm standing while going to Majnu Ka Tila, I will try and look at that direction and go in that direction as much as possible. If that direction does not exist, then I'll go closest to that direction, right? So if I know that, if suppose I'm standing at this point, I'm standing, let's say, at this road, right? Let's say this is the road, and this is where Majnu Ka Tila is, right? Then I'll say, oh, I'll go here, because if I go here or here or here, I have 4 possible options. Maybe this is taking me closer to this than this, right? But it's actually possible that you go here and then there's a turn that goes directly straight. Sure. So this may be the optimal answer in longer run, right? I mean, if I knew before, then I would have gone here and then taken a turn. But chunki I don't know what's going to come here, I'll go this side. Okay, at that point. Are you with me, guys? What I'm trying to tell you is that at that point, you don't know what is lying ahead. How are the turns, right turn, left turn, diagonal, etc. of the road there. Okay, because you don't know the answer beforehand, right? You don't know the path beforehand. So us samay, at that point, you will just stand and say, oh, what is the best locally right now at that point? And that local direction, right? So that local direction, for going from xt to xt plus 1 is basically negative of gradient of f at xt. Okay, now why is that the case? We'll just prove it in 2 lines. It's just a 2-3 line proof. But why am I really getting into these things so deeply? So that you learn one thing, that even though you go in this negative gradient direction, whatever, that may not be the best direction to take always, okay, in the longer run. Okay, and that is where other gradient methods that will do, right, where we don't know, where you don't go to that direction. Okay, really, you go to some other direction which is a function of this gradient direction. That actually makes more sense. Okay, we'll come to that point. And this, remember this example, then you have to remember this example then. Okay, but right now this is what we know, कि locally मैं अगर xt में खड़ा हूं, मुझे सिर्फ xt का gradient calculate करना आता है, मुझे कुछ पता ही नहीं आगे क्या होने वाला है, right? Then I'll go in that direction. Okay, any question? Okay, no? All right. So here is a 2-line proof of the following. It involves directional derivative, which I think I skipped for a reason. But what I'll do is I'll still give you the meaning of directional derivative. It's really not very difficult. Okay, so let's say I have a function fx, right? Now the meaning of if function fx is from r to r, right, then the meaning of derivative, right, which is d by dx of fx, okay, or f prime x, is the following, right? So you take this limit h tending to 0. Okay, you go from x of x plus h to take the difference and this, right? You can go from x minus h to x also. So this is my x. Okay, you can come from x plus h, or you can come from x minus h, right? So there are possibly just 2 directions where you can come from. Okay, and when both exist and they are same, then the function is said to be differentiable, right? So ye r mein hai, ye one dimension meaning of differentiation, right? This is just f dash x in 1 dimension. But if you recall, if fx is this, right, then you basically take the gradient which is in n dimension. So you basically do this. Right? So ये इसमें क्या हो रहा है that you are actually taking the gradient of the function in n different directions corresponding to n axes. Okay, and these axes are canonical bases, right? So 1 0 0 0 1 0 etc. and all that, right? This is the gradient in that basis. On the other hand, you may also want to find out. So this is like, so this is like this thing, rate of change in direction x1, and this is rate of change in direction xn, rate of change in direction xi, right? So there are n rates of change. Are you with me here? So I'm just making 2 points, that when you have an n dimensional function, there is just one rate of change. Okay, but when you have an n dimensional function, there are n rates of changes, right, corresponding to each direction, corresponding to the canonical basis. Is that okay? Is this point clear? अरे भैया बोलोगे?
Yes, sir.
Amisha, is this clear? Hinakshi? Is Hinakshi around? Okay. Raidu?
Yes, sir.
Is this point clear? That when you have a n dimensional function, there are n rates of change?
Yes, sir.
Huh? Yeah?
Yeah.
Okay. So it's like this, right? That I have an n dimensional function, and this is my point x, right? I can measure rate of change from here, and from here, right? Three directions, and all these three rate of changes are encoded in this gradient vector, right? Corresponding to 1, corresponding to 2, and corresponding to 3, right? Now the question is this. Here's my question. What if I say that I want to find the rate of change not in this direction or in this direction, but in actually this direction? I mean, sorry, this is not 3D. Oh, I accidentally made a very good 3D diagram. Never happens when I want to, but always happens when I don't want to, right? So let's say this direction. Let's call this direction V. Okay, V basically is this, some linear combination of these three canonical directions. What if I want to understand what is the rate of change of my function in an arbitrary direction, not on canonical x1, x2, x3, but a function of x1, x2, x3? Okay, which means this is what I want to calculate. Okay, I want to calculate x of tv, okay, minus f of x, okay, t tends to 0, right? This is what I want to calculate. This is the meaning of functional derivative in the direction v, right? Please understand that this function derivative is not a vector, it's a scalar, because I just want to measure the rate of change of my function in that direction, not in all the directions, but in that direction. But that direction is a linear combination of some canonical directions, x1, x2, x3, and all that. Is this point clear, guys? This is a very complicated point. This is not an easy point. Siraj, is this okay? Siraj, where is your friend Moksh?
Sir, I guess he's not well, that is why.
Okay. Nazri? Are you here?
Sir? Ha, sir. Yes.
So what did you understand?
That the directional derivative is a scalar. It's not a vector.
Mm-hmm. Okay.
And
Yeah.
that's it.
That's it. Okay. So, the key point is that you can measure the rate of change of function in any direction. Is that point clear?
Yes, sir.
Right? Okay. Thanks.
Yes.
Okay. Rohit,
Yes, sir.
so do you know that rate, this directional derivative, right? So this so-called directional derivative
Yes.
is basically sort of this.
Yes, so this makes sense. So this is just the projection of the actual of the gradient along the direction you want.
That's absolutely right. That's very nice, right? So that is the meaning. So basically what is happening, right, is this, that we want to find the rate of change of function in this direction, right? This is what we want to find. What we are saying is, okay, why don't you find the rate of change in this direction, this direction, this direction, and just project that. Basically take the angle, right? Because gradient is an angle, gradient is a vector, okay, and the rate of and the direction in which we want to find the rate of change is also a vector. Just take the inner product. So sort of project that vector, which is your gradient vector, in the direction where you want to find the gradient. Okay, so the directional derivative is basically the inner product, right? It's an inner product of this guy, okay, which is a vector, and this guy, which is where you want to find the directional derivative, and the inner product is a scalar. Okay, so I just project it and I say, yeah, ठीक है, linear combination है तो मैं उसे project कर दूंगा. Just like other stuff that we had done before, right? Linear combination, projection कहाँ आ रहा था? Projection आ रहा था वहां पे when we were trying to find the coefficient of anything on a particular direction. We are just finding the inner product, right? If you recall, in the initial days of linear algebra, first week, this is exactly same. This is just finding the coefficient of that vector, which is the directional changes in each direction with v. That's it. That's all it is. Is that okay? If it's not okay, I recommend you just, it's pretty much calculus, second grade calculus, as in second course in calculus is what teaches this directional derivative. Just go and check out. I'm emphasizing on this definition or on this concept is because this is pretty useful. Once you understand this, then a lot of decent algorithms actually just follow this pattern of taking directional derivative and going in some sort of a direction. Okay. Anyways, so that's our directional derivative. Now, again, coming back, this is what we want to prove. Okay, we want to prove that when I go from fx, when I am at xt, f of xt, I want to go to that direction which maximizes my decrease in function, right? Why do we want to maximize my decrease in function? Palak?
Yes, sir.
Why do we want to maximize the decrease in function at xt?
So that we can find the direction in which we need to move next.
No, but why do we care about maximizing the decrease?
So because we move in the direction where there is maximum decrease.
Yeah, I'm saying, why is A good? You're saying A is good. I'm asking you, why is A good? Why do you want to care about decrease?
So because that is the next possible move that we feel, or on a given point we feel that is the next possible move.
Why do we care about that move?
We want to move towards the goal.
Well, okay. The answer is that because we are minimizing the function, and because we are minimizing the function, we want to find that point which is the least value, and to find the point which is the least value, I want to decrease the function. That's it.
So, to reach global minima.
What?
To reach global minima.
No, not to reach global minima. No, to reach a point which has a lower function value than the previous point. That's it.
So ultimately we are reaching towards the global minima, right?
Shantika, in every class you are so interested in global minima. I've told you, please don't have such expectations. You'll never reach global minima unless and until you have a very nice problem in your hand.
Okay.
Okay. Only with convex problem which are strictly convex you can reach global minima. And there also you don't reach global minima. You are at this point. You reach here. It's not global minima. Okay, less than epsilon, right?
Okay.
You're
Okay,
not
sir.
you're
Yeah.
not mathematically, strictly speaking, you can never reach global minima if you don't have infinite precision. Okay, so you just reach a good point, very good point, nice point. It could be as well be very, very close to global minima, as much as possible, close as you want, but not exactly there, right? Okay, great. So now just one line proof. That's it. There's one line is remaining. We'll use Cauchy-Schwarz. Okay, if you remember Cauchy-Schwarz, we'll use that, and that's our proof. Okay, so here is the proof. So I am at, let's say I'm at xt, or let's say I'm at x, right? I'm at xt, sorry. And let's say I don't know which direction to take. So I take this direction v, right? I take this direction v. Okay. And let's say I reach xt plus t times v, where t is my, v is my unit vector in this direction, and t is the length in which I have moved, right? So I reach x of f of tv. Okay. Which means that my decrease in function value, okay, is this guy. Or change in function value, I'm sorry, not decrease in function value, is this guy, right? Okay, any question? Right? And this is sort of the rate of decrease or rate of change in the function value. Okay, actually let me just take a decrease only, so let's call it decrease. This is the decrease, right? Okay, this is the decrease. Now what is this? This is the directional, limit tending to zero, limit t tending to zero, right? If I take limit t tending to zero, this is the rate of negative rate of change of direction in the direction v, which means this is this guy, right? Negative of this guy, because it's opposite of, you see, this is, this is the directional derivative. This is this term is the directional derivative, and this is the rate of, this is the decrease in function value, right? So this thing is this, because this thing is the directional derivative, correct? So therefore this thing is the negative of that, right? Now the question is, what is v? We have not decided on v yet, right? So what is v? V is something that maximizes this term, whole term. Now what is Cauchy-Schwarz? Do you recall what is Cauchy-Schwarz? Anybody?
So
Sachin Sharma? Sachin? Yeah, I want to understand how many people are actually here. So those who are here, can you please raise your hands? Okay, so there are 25 people. Okay, let's see who is not here. Zubair is here. Okay. अरे सभी लोग हैं here. Mayank is not here. Oh, Mayank is also here. Dipanshu and Santika. Santika is here. Dipanshu. Dipanshu is has muted and
Yes, sir,
reduced
I'm
the
also
volume.
here.
You're here.
Yeah.
Oh, okay. You're not able to raise your hand, is it?
Yeah, I couldn't figure that out. I guess I have older version of Zoom.
Oh, I see. तो सब लोग हैं. Okay, fine. ठीक है. So somebody, no, I'm happy to see this. Thanks. So Tanay, yeah, please go ahead, Tanay.
So the Cauchy-Schwarz inequality is basically the inner product is less than equal to the individual norms of L1 norms of the elements.
And greater than
multiplication.
equal to?
I mean, like right now we have the expression that the inner product of gradient of fx comma v. So it will be less than equal to the L1 norm of gradient of fx into L1 norm of v.
Right. So thanks. Thank you. So, basically it says this, right? That A, B, okay, is less than equal to norm of A times norm of B, and also greater than equal to minus of norm of A times norm of B, right? So this is the lower bound and this is the upper bound, right? So we want to minimize this, right? We want to have this as maximum, right? Because this is the decrease in function. So we want to have this as maximum, which means this term should be minimum, which means if I take V as minus of gradient of fx, okay, then the whole thing, jo andar ka jo this box, right? This box is minimum and the overall thing is maximum, which means this is my, direction. Of course, because V is a unit vector, so I have to divide by the norm of this vector. So V is minus gradient of fx upon norm of fx. It's a unit vector in the direction of negative of the gradient. Okay, is the one that maximizes my decrease in function value when I am at xt. Is that okay? This is, by the way, xt. All of it is xt. Is that okay, guys?
Sir, can you repeat this last part?
Okay, so let me just write this again. So you know, right, that the decrease in function value is this. Is that okay?
Yes, sir.
Why is that the case?
Sir, because
that's a directional derivative.
yes, sir, directional derivative.
Right. Now I want to find V. Remember, मैंने V निकाला नहीं है अभी तक.
Yes, sir.
Right? I've taken some V. I want to find that V, right? So that will maximize this guy, right? The whole thing.
Sir, including the minus sign outside.
Including the minus sign. Yes, including the minus sign. This is a red thing, right? Now there is a blue inside it also, right? Or blue or whatever, green, right? This.
Yes, sir.
तो पूरे को मैक्सिमाइज करने के लिए अंदर वाले को मिनिमाइज करना पड़ेगा, because this is a negative outside.
Yes, sir. Yes, sir.
What is the minimum of the inner product of two vectors when they are in the opposite direction of each other?
Yes, sir.
Right, which means V is this guy. That's it.
Okay.
You
sir.
see, V is in the opposite direction. V is in opposite of this, right?
Yes, sir.
That's it. That is why the negative of gradient. So you move in the negative of gradient. That's it. That's the answer. Okay. So that is what gradient descent is. Itna hi simple hai. That I am at xt. To get to xt plus 1, I move, right? Basically xt, I'll move in some direction, okay, of the negative of gradient, right? Remember I said I'm going from xt to xt plus tv, okay? But v is negative of gradient, right? So I'm moving from xt to xt minus this guy. I multiplied by gamma t. Basically, I'm saying that, well, what is gamma t? I have first found a direction in which I want to move, but I've not found the length of that move, right? So gamma t is giving me the length. So that's it, right? So xt plus 1 is xt minus some length that I want to move times the direction in which I'm moving. That's it. That's your gradient descent. Okay. Folks, is it clear?
Sir, gamma t is the scalar.
Gamma t is the scalar. Gamma t is the scalar,
Okay.
yes.
And
Okay. एक second. Let me just, elaborate a little further. Okay. What have we known so far? What have we known? Right? This is what we know. Okay. We know that we started with x0, then we want to go from x0 to x1. But how do we know that we are getting closer to optimal? Then we said that, well, we'll know we are getting closer to the optimal if I know that I'm going in the right direction. Okay. Then what is the right direction? The right direction is the direction in moving at the negative of the gradient. Okay. Which means if I'm at x0, I want to move from x0 to this direction, right? This direction. Right? Because v was negative of gradient x0 by norm of gradient of fx0, right? Okay? Soumya,
yes,
is
sir.
it okay?
Yes, sir.
Yahi to tha na?
Yes, sir.
Now I'm saying that define t by this thing as gamma t. Okay? Then I say x1 is x0 minus gamma t times this.
Yes, sir.
That's it. That's it. Now the question is this. Siraj, a question for you, Siraj.
Yes, sir.
How do you know that this will, by doing this, you will reach, you'll reach our goal? What was our goal? This was our goal.
Reaching the optimal, like the minimum value of the function.
No. Yeah, this was our goal.
Yes, sir.
How do you know that if I keep on doing this, I'll
Sir,
reach here?
so yes, sir. So the function value will keep on decreasing if we keep on moving.
No. Wait. No, the function value does not mean it absolutely does not mean that it will keep on decreasing, because the gradient is the direction of local minimum, right?
Right.
But it is not saying that the function value will decrease automatically if you move any length in that direction.
It's like we have to move very small length.
Right. So you guys just please understand this point, right? So suppose now I'm drawing this function. Suppose this is my function. Okay. Suppose I'm here, right? So this is the gradient direction. This is a negative gradient. Now I can move this length. 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 All of this is negative of the gradient direction. Now suppose I move this length. Then I'm at this point. Okay. And my function value is here. It has actually higher value than this point. Is this okay?
Yes, sir.
Siraj?
Yes,
Sahi hai na?
Yes.
Everybody is convinced? Ratna, Sai, Kiran?
Yes, sir.
Are you convinced that I can actually move in the negative gradient direction and yet my function value may increase
Yes, sir. It can increase
It can
because
increase.
yes, we can. It might happen that we'll take a greater length. We'll be
Yeah.
skipping the local minima.
अरे local minimum वगैरह तो बहुत दूर की बात है. We are not even decreasing our function value. Forget about local minima.
Yes, sir.
Right?
Yes.
Okay, so Siraj, the question is, how do you know that it will, you'll reach a good point by doing this method?
So if we take very small steps,
हाँ.
so तब तो function की value decrease होती रहेगी, like, और I guess कि फिर एक point पर आके we will start getting the gradient 0, तो हम move करना बंद कर देंगे.
Gradient 0 तो भी आया नहीं है. We have not even proved that yet, right?
Sir,
Yes, you're right. Yes, you're right. But yeah, go ahead.
Sir, that condition we wrote that it should be less than some value.
But we don't know.
Epsilon.
But we don't know that value. That's the trickiest part.
So maybe we can check where this difference starts to increase again.
Which difference?
This fx fxn. Okay, yes, we don't know the fx star.
Yeah, but but you're right. We don't know fx star, but we know x of n+1, right? I mean, we know
yes,
x
we
of
know
t+1.
Yes, so we can check if in the consecutive 2 points we are getting like instead of decrease we are expecting an increase.
Right. So one way is that I take some length, I check if the function value is decreased, I accept that length. If the function value is not decreased, I take a smaller length, right? And I keep on doing that. That's what you're saying, Soumya?
Yes, sir.
Okay. All right. Rashid, yeah.
Yes, sir. I was saying that just like what if we keep track of the best value we have reached, the minimum function value that we've reached till now, and
Absolutely.
and every further iteration we just see if it's better than our current minimum value.
Absolutely. You can do that also. You can do all of it, right? And that is where the various, I'll say various versions, or, I don't know if you have played this, poker, right? So, or, in Hindi, we call it teen patti, right? So
Yes, sir.
there are variants, right? So this gradient descent is also like playing poker with your, with your adversary, which is your objective function. And you keep on asking right questions to that guy, right? And you keep on changing your strategy based on what you learn for that guy. Okay. And then you decide on the optimal strategy based on the nature of the guy, the nature of, how he plays, right? So convexity, non-convexity, strictly smooth, all that, so based on that, you have 5 or 6 like main features of that person, of that objective function, and you decide based on that, right? And this is exactly what this course will be all about in the coming weeks. Okay, we'll see that. In the next class, we'll actually prove that under certain conditions, gradient descent actually always converges, and we don't have to do all the stuff that we actually mentioned just now, like Soumya mentioned or you mentioned. But those conditions don't come always. So we'll see when do they come, when don't they come, and we'll basically sort of segregate these cases and keep on evolving our algorithms for more and more functions and for more and more broader class of objective functions. All right, so that will be a strategy. We will see that in the coming classes. Okay. All right. Any question?
So for now, we can do only 2 things. One, that limit the value of gamma t so that we are not moving very faster, and also check for all updated values of xt+1 whether the value of function is decreasing or not, right? Only 2.
That's right. That's right. That is all we know. That's
okay.
Right. So now I want you guys to go back and write a Python code for this, right? Just take this objective function if you like. Okay, take this function, the function that I discussed in the beginning of the class. This function, take this function and write a code for this, right? This guy. Okay. Find the gradient. You know how to find the gradient of this, right? We have done that in the class, in the calculus class. Find the gradient of this guy. Okay. And keep on, going in that gradient direction. Check whether your function value is decreasing and all that. Do that. And hopefully, in the next class, I'll also ask you to share your screens to look at your code, how you're writing it, etc. So we'll do some coding also together. Okay. We'll take it slow, but we'll code it. Okay. Next class, next class, mujhe pata nahi kab, but we'll do that. But you know enough now to take any objective function which is an unconstrained optimization problem. Look, we have not done constrained optimization problem. I have not told you all those terms, but look at the objective function and try to take its gradient and then take a random x0 and then go from x0 to x1 in that direction and all that, right? Try to do that. Okay. You are now fit to write code, by the way, all of you. So likhna chalu karo. ठीक है? Okay. Any other question, folks?
Sir, can you please show the last page where we wrote the gradient descent?
Yeah.
Okay. So in this we have already discussed about directional descent also, right? I mean, throughout this explanation, so it is clear that the other term, where we started, that is called directional descent, right?
Directional descent.
Yes.
I mean, every descent is in a certain direction. So yes, yeah. I mean, this is also called steepest descent, etc. But are you referring to those terms and then making a difference here?
Yeah, maybe because so the previous time I have gone through this. So first we started with directional descent, then we went to gradient descent, and the only difference I found out that was in directional descent we took a scalar, and in a gradient descent we took a vector. So this is I mean, yeah, this is why it is right. In directional descent it is a scalar, right?
Yes. I mean, I hope I'm getting your question, but yes.
Yes. Okay.
So we didn't know which direction to go. Then we found out our direction, and now we are going in that direction. That's all we have done.
Okay, sir. So we are saying this step size is t by norm of del. I mean the gradient of f of x0, right?
Yeah.
Okay.
Yeah. But that's the point, that this thing will disappear soon.
Okay.
Because this is just to normalize the direction and make it a unit vector. But because we don't care about unit vector, because as soon as we multiply it with the scalar, the length changes. So all we care about is the length in that direction rather than the length of the vector itself.
Okay. Okay, sir. Yes, that's clear. Yes.
Okay. By the way, this is also called in machine learning rate. Okay, this is also called learning rate. How much are we learning? I don't know why they called it learning rate. This is beyond me, because this is not learning anything. But ठीक है, उनको अच्छा लगता है सब terms बोलना, तो बोल रहे हैं, ठीक है. I call it step size, but machine learning folks always invent stuff that was invented 50 times before and make it a new thing so that they can publish more and be more cool, right? So sure. But by the way, all of it that we've done was actually discovered in 40s and 50s by Russian scientists. They wrote Russian papers in Russian, that is, and then Americans as usual came. They made it look like as if they have invented it. Of course, von Neumann, etc., did work on these things, and they did do something in around the Second World War. But the great Russian scientists, Nestorov, Nemirovsky, they've actually done a lot of work already by 70s and mid 70s and 80s. Okay, then this ML folks and all these American folks came. I mean, I'm absolutely not anti-America, and we should not record all of this here, but you would know that a lot of stuff that is now, you know, offered as ML and AI, etc., was actually done long back. Just, you know, it was made more approachable and more applicable to the current stuff, and therefore, you know, a lot of reinvention of V, by the way. So, okay, great, thank you.
Sir,
Yeah.
sir, I had a few